Very good morning, all of you. So in the last previous classes, we have been discussing some of the interesting concepts in the course Strength of Materials. Okay, so we understood the concept of center of gravity for bodies having masses. And then, so we related the well in concentrated, we connected with the term centroid. Okay, so what is the centroid? So for plane figures having only areas without masses, that is, for plane figures are laminas. Having only areas, no mass. So these are the two terms we have differentiated, and we came to understand the center of gravity for bodies of having mass, and then what is the centroid for areas or plane figures having only areas. This is an important term. Okay, the centroid of an area plays an important role in mechanics of solids and mechanics of fluids. And then we came to know what are the different methods of finding a centroid, especially methods of finding centroid for some important laminas. Okay, so that is, we came to know that the first one is by mathematical or graphical method, or by some means of geometrical considerations. And then we came to know by method of moments method, and third one is graphical method. So out of these two, we have seen one by one what is the way of finding centroid for a for plane figures by using geometrical considerations in the last class, and then by using moments method we found some geometrical centroid for some of the geometrical plane figures. Okay, so then further we moved on to the finding the geometric center for, that is, geometric center are nothing but the centroid for some important plane figures like rectangle, square, triangle, trapezium, half square, semicircle, and then sector. So we found the geometric centroid for some important plane laminas. Okay, and then at the last we solved in determining the location of a centroid or position of a centroid for one of the important engineering section like T section, that is determination of centroid or location or position of the centroid, right, for an engineering section like T section. So we have solved this one problem with an example. Okay, so how to locate the centroid for this T section for the given dimensions in the last class. Okay, I hope you have understood all these concepts in the last class what we have discussed. Okay, the today's class, so we're going to solve further the centroid for another engineering sections like L, channel, and I sections. Okay, so let's start with the today's class with an illustration of this formula in problem next one. So take out the new problem on I section. So we have to locate position of a centroid. This you can see in the image. We have important sections, engineering section like I section, next channel section, and L section and T section. We have already dealt the problem on T section in the last class. Okay, now we are going to start with another illustration example on I section. Okay, so take out this data of the problem. Okay, so determine mathematically the position of centroid of an I section as the following units in millimeter units. So it has bottom flange of 300 into 100 millimeters, web of 300 into 50 millimeters and top flange of 150 into 50 millimeters. For this cross sectional of given dimensions, we need to locate the position of a centroid for this given I section lamina. So let's see how we are going to solve this. Okay. So first, write out the schematic, or as it is, just copy the image. Okay. So the given I section is of an bottom flange of 300 into 100. So I'm going to write this bottom flange. Okay. Next, and given web is there. So mark it this of given cross sections, bottom flange of 300 plus 100. Okay. So this is 300. All units are in mm. Okay, and this is 100 given the data. So next, to web dimensions they have given 300 plus 50. So let's write the axis, one axis here, to midpoint of this rectangle. Okay, so just I'm going to write the web here. So the dimensions of this is given. Okay, so this is the height is 300 and breadth is 50 mm. The same I'm going to write here. Okay, and then this is the 50. We take out this breadth, and then given the top flange of 150 cross 50, so write out the another flange. So it has just 150. Okay. So this is the I section for the given dimensions. So this is given as 150 mm of length and then 50 mm of breadth or width. Okay. So we need to locate a centroid for this given I section lamina. As you can observe in the schematic. Okay. So this I section lamina is composed of 3 different plane figures. That is, it is of 3 different rectangles, isn't it? So first, individually we have to calculate the centroidal distances or centroids of these individual laminas. Then, so sum of these individual areas and then product of those centroidal distance by its total area will give you the centroid of this given I section lamina. Okay. So next, the first step is to divide this I section lamina into 3 individual laminas. That is, in terms of rectangles, I give namely this as 1. Okay, the bottom flange as 1, and then web is of 2, and top flange is of 3. Okay, just I'll name them as okay, A, B, C, D, right? E, F, G, and H, and then last top flange I, J, K, L. Okay. Just in the first step of the problem, I divided this lamina into 3 cross sections of rectangles. I mean 3 different rectangles of first rectangle of ABCD. Okay. The cross section 300 into 100. Okay. And then the second is web. Okay. It is also an rectangle. This cross section of EFGH. So this cross section dimensions are 50 cross 300, and then another rectangle. So IJKL. So its dimensions are 150 cross. So this is the first step. We have to do it. Okay. So dividing the given whole lamina or the whole complete figure into individual plane laminas or individual figures that we have done here. So next, we have to check out the axis of symmetry, whether the given I section is symmetrical to XX or YY axis. So axis of symmetry, as we have seen in the last class, okay, it is the plane which divides the area of the lamina into two equal, it distributes the area into equally on its both the sides of the plane. That means, so it looks like a mirror image. For example, if you take the axis of symmetry along the x-axis, just I'm passing the axis here. Okay, whether this axis is dividing this whole area into equal parts? No, obviously no, because the top flange is of lesser dimensions and the bottom flange is of 300 dimensions. The area below this axis is more and area is lesser in this. Okay, so that's why if this top flange is of 300 so then the given I section would have been symmetrical to x-axis. But in this case, okay, the given top flange is lesser, so therefore, if the x-axis is not dividing the given I section area into two equal parts. It is not obtaining like a mirror image. So let's check it out in this particular axis, in YY axis, as I'm writing here. See, exactly you can observe this. So this bisecting this whole lamina into two equal parts, and that means this distributing this given I section into two equal areas. Okay, so on this side, on either side of the plane, okay, the areas are equally distributed. That's why, so the given I section is symmetrical to YY axis. So that is the second step we have to consider, right? So the given I section is symmetrical to YY axis. As we discussed in the last class, if any one of the section or plane lamina is symmetrical to any one of the axes, okay, then the point of centroid or the position of centroid will be located on its axis of symmetry. That means the point of centroid for this I section will be will be lying in this axis only. So then it is unnecessary to calculate the x coordinates. Okay, we need to calculate the y coordinates of this I section. Thereby, we can locate at what distance, okay, in the vertical direction the position of a centroid is located. Okay, that is the second step. We have to just do it, and then the third one. Okay, so we have to consider the reference axis, any one of the reference axis. As we came to know in the last classes, okay, the bottommost line will be the reference axis for y coordinates, and the leftmost line will be the reference axis for x coordinates. Okay, here we doesn't need any x coordinates. So as I said, okay, it is symmetrical about the y axis. The point will be located on y axis itself. So this bottom axis, that is, I'll call up this as, okay, xx, right? So this is an reference axis. I'm writing here. So this is the reference axis for finding the y coordinates. Okay, that is for locating the centroid for this I section. Okay, so next, take out the finding the coordinates or the centroidal distances of these individual laminas about this reference axis in the next step. The first, I'll write here a serial number. I hope you can see this. Okay, so plane laminas are plane figures as listed in the top already. Then area in millimeters square. So the centroidal distance, that is in terms of y coordinate. So that is right. So this is y coordinate, and the product of these two we need, that is a into y. You can write here. So this is in mm, the distance, and then this is in mm, right? So let's find one by one for each laminas. So this method is a bit simpler, so it avoids the confusion of the students to follow this. And another method we have presented in the slides. You can refer whatever the thing you want, which you feel comfortable. Okay. So the first plane figure, as we have considered, the number is 1. Okay, so let's take out the same. The first one, the plane lamina is ABCD. It is a rectangle. The shape of lamina is rectangle. Okay, so rectangle ABCD is our cross section. So it is mentioned length 300, breadth 100. That is 300 plus 100. Then the area of this rectangle is L into B. We know that. So we can take that A1, right? Area of the first rectangle. So that is 300 into 100. We'll get an 3. So the value, so 30,000, right? Of millimeters square. Then the centroidal distance for this rectangle ABCD, okay, it will be half of its B by 2. It's half of its breadth. So the breadth is 100. Okay, the first y1 is here. You can say half of this breadth. Okay, 100 by 2. That is y1 is 100 by 2. In mm, it is 50. Okay, so when we multiply these two, so 30,000 into 50. Okay, 33 5 is 15. Okay, so that is around, you will get 15 lakh. Let's say 15,000,000. Okay, so that is one we coordinate and area we found. Okay, we came to know of one of bottom flange ABCD. In a similar way, so let's get the coordinates, y coordinates of this web, that is EFGH. Okay, and its area. So coming to that, okay, so the area, I mean that another plane lamina is also, it looks like a rectangle. Yes, the shape is rectangle. You can write that. So rectangle is named as EFGH. So our cross sections they are given, right? The length is 50 and breadth is 300. So 50 cross 300. Okay. So the area of this web is A2 is given by length into breadth. The formula of rectangle, we know that. Okay. So that is 50 into 300. You'll get nearly, so 15,000 millimeters square as area in mm square. So next find the centroidal distance of this plane lamina about and reference axis XX. That is the bottommost line of the I section. Okay, we know this from this to here. So the centroidal distance will be for a rectangle will be its above breadth, that is 300 by 2. So that is from here to here you have 150. From here to here you have 100. Right. So that is, so from when we go from the bottom. So 100 plus here 300 by 2. The same I'm writing here. So bottom flange width is 100 plus half of its breadth 300 by 2. So that is 150. So 150 plus 100 is 250 in mm. So product of these two, A2 and Y2, will get around 375. So 0000. So this is the value after multiplying this area of this web with its centroidal distance. In the same manner, when we look out in finding the area and centroidal distance for the top flange of IJKL, so it is also rectangle, as you can observe, and the bold. So the rectangle IJKL, so of cross sections, the length is 150 and breadth is 50. Right? So its area A3, so length into breadth is the formula. So 150 into 50, so 7,500 millimeters square. Similarly, when we look out the centroidal distance of this top flange from the reference axis XX, that is the bottommost line. So this is the Y3. I'm going to mark this. So this has been the Y1 already. So half of its depth, breadth, whatever it is. Okay. So this one is the Y1. We already found as 50, 100 by 2, and then this is the Y2. So this is 100 plus 300 by 2, 150, already calculated from the bottommost line. Now we are going to determine this centroidal distance of this plane lamina 3, that is top flange for given I section. So this has been the Y3 for this. So find out the distance or centroidal distance of this length from the bottommost axis. That is from here to here we have 100, then plus 300, that is 400, plus 50 by 2. That is, so 450 by 2, and you will get it as 425. So write it here. So y3 is, I'm going to calculate it as 100 from the bottommost line plus 300, okay, plus here half of its breadth, that is 50 by 2. The centroidal distance for rectangle, as per our geometrical considerations, we came to know. So the centroidal will be lying its half of its breadth and half of its length. That is the point, right? So based on that, we came to know this, the y3 centroidal distance of this top flange around 400 plus 50 by 2. That is, so 425 millimeters. Okay. So just product of these two, A3 and Y3, will be in numbers as 3187500. Okay. So these are the coordinates. First in the next correspondingly we calculated for this given I section. So based on this data, we can determine the centroid, okay, of this given I section as by method of moments. So first I'm gonna take this whole area of the I section, that is summation of area is equal to A1 plus A2 plus A3, that is 30,000, right, plus 15,000 plus 7,500, which given me as the value of 52,500. So of mm square of area we calculate. Similarly, the product of its area and its centroidal distances of all the laminas, that is summation of, right, A into Y. So Y coordinates only we have calculated. It's given by adding all these values. That is 3 lakh, 37 lakh 50,000, and this 3187500. So after all this, we'll get a value of 8437500 in mm. Okay, so we know from the formula, right? So the centroid for a whole section or given I section is calculated by the known formula. So by the method of moment, so that is y coordinate is given by, with reference to x axis, is equal to summation of its area into its centroidal distances by its total area. Okay, so that is nothing but, so in simple word, so A1 into Y1 plus A2 into Y2 plus A3 into Y3 by upon A1 plus A2 plus A3. So this value A1 Y1 plus A2 Y2 plus A3 Y3, right, is done here. Okay, and then the total area is calculated here. Just substitute the known values in the above equation. The summation of product of its area and into its centroidal distance, we have the values here. So 8437500 upon the total area of this I section lamina is 52,500. So thereby we get an y coordinate of distance, so 160.7 mm. So this is the value, the centroidal position of a or the position of a centroid for this given I section lamina. Okay, so no need of x coordinate because here, so this is symmetrical to y axis. The point will be lying on this y axis only. Just locate the 160.7 from this reference axis about xx. So around you will take it as, so this is 150 from here y1 y2. So just above somewhere here 160.7 means just by mathematically we can assume this. Oh, this is the point C, our center of gravity, our centroid. For this I section lamina, I'll write this y bar is equal to 160.7. So from particular distance with reference to this axis, bottommost one. Okay. So that means, so this is the point. Okay. So at 160.7 mm about its y axis, the whole area, that is 52,500 mm of area of this I section is assumed to be concentrated at this particular point. Okay, so the centroid for this given I section is located at this point, that is at a distance of 160.7 mm from the bottommost line, that is from the reference axis x. Thereby, we found or we located the position of a centroid for this given I section lamina. Now, hope it is clear. This problem you can solve it. It is an important problem you can experience in your examinations. Okay. So in the first step, we have to divide it into 3 individual laminas. Then later on, you have to check out whether the given section is symmetrical to XX or YY axis. Based on that, so we need to locate this coordinates. Okay. So X bar or Y bar coordinates. In this case, it is symmetrical to YY axis. We are going to calculate it. I mean, we calculated only the Y coordinates, that is Y bar. So then we have located this centroidal point on the YY axis. Okay, that is at a distance of 160.7 mm. The whole area of this I section, that is 52,500 millimeters square, are assumed to be concentrated on this point. Okay, so next we're going to look with another problem. So let's take out the channel section. As you look in the slide, okay. So take out the channel section. This is the next problem. Okay. So the channel section is given for 100 into 50 into 15, 15 mm. Okay. So let's take a just look at this problem. So just copy the data as they are given in the problem without any errors. Just I'm going to write this given channel section as it is. Okay, its dimensions are given as 150, 100 height, 50 width, and 15 mm thickness. Just I'm going to measure that. So this is height of 100. Okay, then 50 width. So then thickness of 15. Thickness is given here, or else I'll measure here 15. The same is here also the 15, and this is also 15. You can mention that too. Right, and then so here also the 15 width of this channel section. So we are looking out the important engineering sections like T section as already seen, and then I section in the last problem. Now we are going to solve the channel section. So yes, given a figure is for the given units we have dimension. Now check out the this channel section has to be divided into individual laminas. Okay, I'll go one by one. So this is A, B, C, D. The first one I'll locate that this is 1, right? And then this is 2, and this is 3. So I divided this given whole lamina of channel section into 3 individual plane laminas. So I'll name them as A, B, C, D here. And then this is D, E, F, G. Okay. And then G, H, I, J. Okay. So that's, I'll write here. Okay. So first, the given lamina is divided into 3 individual laminas or plane figures. Okay. The first one is a rectangle ABCD. Okay. So cross sections is its length is 50 into its breadth is 50. Similar way, so another rectangle. You take the cross sections of this rectangle. I'm going to mention here itself. Okay, I'm considering this DEFG as a one rectangle. Okay, so that is 100 minus 15 minus 15. So both the sides it is subtracted with 15. Okay, that is 100 minus 30 will give you the its cross section 70. So that is this distance is 70. After subtracting 15 from the top and 15 from the bottom, okay, so we'll have an its breadth of 15, 70, and then its length is 15 mm is given. Okay. So another rectangle of DEFG. So this cross section is 15 into 70. You have to be clear in these dimensions. If you make the mistake in the beginning itself, then the entire problem will go into the wrong. You will lose the marks. And another one is the last one, GHIJ. Okay, it is also in the form of rectangle, isn't it? So that is GHIJ. So its cross sections are the same, 50 into 15. It is the same. So 50 into 15. So hence we have divided the one complete whole lamina into three individual laminas. Then we have to check out the axis of symmetry of this plane lamina. So whether it is symmetrical to x-axis or y-y axis. So let's divide it to its midpoint, that is 50 is there. Just say I'm dividing this to 25 mm distance. Okay. So like this. Okay. This is I call up as y-y. Whether again, as you observe, whether this axis is dividing this area into equal parts, two equal parts. Just look out the channel section. So whether this axis, or I'm just cutting this section, channel section with this plane, y. Okay. So this plane is not dividing this given channel section into two equal parts. It is not divided into two equal areas. So that is, this is not symmetrical about y axis, because it is not distributing the area of this whole section into two equal parts. Okay, so we cannot consider the given section is not symmetrical to y axis. So let's take with the x. Okay, so this is the plane or axis passing through its midpoint. Okay, so as you observe now, so this dividing this area, whole area of this lamina into two equal parts. It is equally symmetrically distributing the area of this channel section. So that's why it is symmetrical about the x-axis axis. That is, we can write x-axis is the axis of symmetry. So that means what? So the location of centroid or centroidal point will be lying on this symmetrical axis, as we from the previous discussions. Okay. So that means we have to calculate only the x coordinates, no need of calculating the y coordinates. Okay, let's take out some in the third step. We have to consider the axis of symmetry. So as we came to know that the channel section is symmetrical to x axis, we need to calculate only x coordinates. Then we need this line as an axis of reference. That is the leftmost line. So just I'll consider this as the axis of reference. Okay, so this is y. I'll write. So this is a reference axis. I'm writing. So leftmost line of this channel section is considered as a axis of reference. Okay. Then let's find out the x coordinates of this channel section in order to determine the centroidal or location of centroid for the channel section. So now the same tabular column we can write out serial number, plane lamina. So individually also we can calculate one by one. Okay. So but in this way we can avoid the confusions, especially for students. Right, and then areas or area of this whole section in millimeters per. The dimensions are in millimeters in the data. So that is 100 into 50 into 15 mm. You have to check out this one also. It is given in millimeters. So next, centroidal distance. So that is The centroidal distances are x coordinates in this case. So this is symmetrical to x axis. X coordinate I'm writing right in mm. So there's next product of these two, a into x in mm. So let's find one by one for each of the plane lambdas. Okay, the first consider first lamina. It is in the form of rectangle ABCD. Okay, it's having a cross sections as I mentioned here, 50 into 15. So the area we know the formula. So A1 is for rectangle is L into B. It is simple. Okay, so 50 into 15. So 7,500. This is A1. Sorry, 750. Okay. Similarly, so find out the x coordinate for this plane lamina. Okay. So it is given the length is 50. We know that for rectangle, the centroidal distance or centroidal point for rectangle by geometrical considerations will be its diagonals meet at the point where its diagonals meet. That is its half of its length and its half of its breadth. We have to calculate x coordinate. Just we consider x part of this. So that is half of its length. That is half of 50 by 2. That is x1. You can say, okay, that is 50 is given. So 50 by 2. At this distance, the centroidal will be located for this rectangle. So we can say the 25. Okay. So product of these two, a1 into x1, that is 750 into 25. Around you will have 1870. Okay. In the same manner, you can look out for the another plane figure, that is it is also in rectangle DEFG. So of cross sections 70 into 15. Okay. So its area is given by the same formula 70 into 15 is given by so 1050. Right? Its centroidal distance from the reference axis y1. Okay. So it's equal to half of its breadth. That is 15 is the breadth given. I mean length is given. Okay. So 15 by 2 will be the centroidal distance for this DEFG rectangle about this reference axis y1. Okay. So that is so 15 by 2. X2 is 15 by 2, which is equal to 7.5. So product of these two, A2 into X2, will get by multiplying this 7875 as in value. So in the last one, so third lamina, it is also in the form of rectangle as we seen. Okay, so GHIJ. Okay, its cross sections are 50 into 15. So this length is 50 and this is 15. So as we mentioned here, it is applies to same also. So area of this rectangle will be A3 is equal to 50 into 15, the same. So 750 millimeters square. So its centroidal distance from the reference axis YY along the x direction. So it is equal to half of its length, that is 50 by 2. So x3 is equal to 50 by 2, that is 25. So multiplying these two will get 18,750. So now, so find out the sum of product of its area into centroidal distance and sum of its area. That is sum of A into X is equal to just adding these three laminas product distances and its areas. Okay. So 18,750 plus 7,875 and then 18,750 will get 4,537. And then sum of its area. So area of all the individual laminas. So 750 plus 750 plus 1050 will be equal to 2550. So now in the next step we need to apply the formula we know from the formula, so by method of moments, we came to know, so x coordinate, okay, will be is equal to summation of the product of its areas into its centroidal distances. That is in x, this is symmetrical to x axis upon total area. Okay, so before that, just locate the distances here. So x1 is 25, for this is 25, x1 25 mm, half of its length. Okay, next x2 is 15, so 15 by 2, 7.5. This is x2, and similarly x3, this one. So that is 50 by 2 is 25. The figure. Okay, just substitute these values as we already know this. So 45375 upon the total area is 2450. So after simplifying this, we get an x coordinate value of 17.8 mm. So this is in mm cube. Okay, so going to the units. So product of area into x coordinate is in mm cube. Okay, and the area is in mm square. So upon cancelling this, we'll get an 17.8 mm, the remaining part. So this is the centroidal distance for this given channel section lamina of given cross sections. So now locate 17.8. So this is the length, or this is the breadth of this channel section. 15 is there, just around, just above this, somewhere here. So take out this as C. So from the reference line, so x bar is equal to, and right here, x bar is equal to 17.8. So this is the point. So I'm supposed to mention between the figures, but let me write just outside the boundary. So now around somewhere. So x bar is 17.8. So this is the position of the centroid. So as you see, this point is just located outside the area of this channel section. Yes, it is possible because of unsymmetry of this section. Okay, and it's given cross sections, so it can be located outside of this area. In the channel section, the point is located just outside this area. And sometimes for curves or for some unsymmetrical sections, the point will be located about just outside this area in this particular case. So that means the total area, so 2550 of this channel section is assumed to be concentrated at this point. Okay, at a distance of 17.8 from the reference axis, that is YY. Okay, so I hope you understood this problem also. So how to locate the channel section centroid for a given channel section. Now, the next problem you're going to solve with another engineering section like L section. It is an example of unsymmetrical section. It is not symmetrical about any of XX and YY axis. Yes. Okay. So just look at this given L section. I hope it is clear, this problem. All of you have understood. Now let's copy the L section, given L section. This is also one of the important engineering section as we come across in structures. Okay, so copy the problem. I'm gonna write this L section. Okay, these are the cross sections they have given 100 into 50 into 20. That height is 100 and length is 50, thickness is 20 in terms of millimeters. So 100 into 50 into 20 in millimeters. Okay, so this is now. So write down the dimensions for this 100. This is 50. Oh, 80. Yeah. Sorry, it is 80. Excuse me for this. So this is 80. Yes, exactly. So now the thickness is 20. So now, as we have done in previous cases, just divide this lamina into two parts. That is one taken as one lamina as rectangle and another lamina as also in the form of rectangle. Okay. So now just name them as A, B, and this part is C and D. Okay. So next, so another lamina C, E, F, G. Okay. Just consider this as one rectangle, that is 100 cross 20. Okay. So the another part of this rectangle is from to start from here C, E, F, G. Okay. So that is 80. So minus of this 20 will be the dimension length for this second rectangle. That is 80 minus 20 is 60. Okay. So now write the so the lamina given L section lamina is divided into two parts, that is in the form of rectangle ABCD, that is 100 into 20. Okay, and then in the second rectangle it is CEFG. So that is 60 into 20. Okay, so now so check out whether this given L section is symmetrical to any one of the axes. That is, if we divide this 80 by 2 in this way, okay, exactly at 40 mm distance. So as you observe, whether this axis, say this is y1, whether this axis is dividing the whole area into equal distribution parts, equal parts, whether on either side of this axis the area of is one is equal to area of the two. No. Okay, it is not looking like a mirror image. That's why it says that the given L section is not symmetrical about the y axis. Okay, so similar way, so just approach with the x axis or x plane. So I'll pass exactly at 50 mm distance. See, area of this portion are equal, whether it is equal to this portion. No. So the area is less in this case and the area is more in this case. Okay. So that's why this x-axis is also not distributing the areas of this whole lamina. Okay. So that's why this axis is also not symmetry. That is, the lamina is not symmetrical to any one of the given x-axis or y axis. Okay. It is unsymmetrical in nature. So in this case, we have to calculate both. In order to locate the centroid of this L section lamina, we have to calculate both x bar and y bar, both x and y coordinates we have to calculate. So next, in the third step, we have to take one reference axis. So bottommost line of the channel section will form the x axis. So this is the reference axis, and the leftmost line will be the reference axis for y coordinates. This is y. Okay, so I'll write this is the reference axis for calculating the x coordinates. This is the reference axis for calculating the y coordinates. So in order to locate a centroid for given L sections, it may take two coordinates or three coordinates based on the given symmetrical sections as symmetry. Okay. Now let's find out the individual x and y coordinates for this given lamina. Right. So it's the same serial number, plane laminas, area in millimeter square, and then centroidal x distance, and then along with this we have to write centroidal y distance. Distance, that is y coordinate. So also in mm. Okay. So next, area into x and area into y. So right. So this is a into x and a into y. Okay, first we go with this rectangle lamina ABCD. Okay. So it is of cross sections 20 cross 100. Okay. So area of this will be 20 into 100. That is 2000 millimeter square. Okay. So next, find out the centroidal distance of this lamina about the reference axis y1. So we know that it will be lying in the half of its length. That is, length is 20. Okay, this is the x1. Okay, 20 by 2. As we report in the schematic. Okay, the x coordinate will be half of its length, right? In the x direction. Okay, its length is 20. 20 by 2. So x1 is 20 by 2, that is 10. Similarly, so from the reference axis xx, bottommost line, okay, so its y coordinate, that is y1, you can look at here, y1, so is equal to 100 by 2, it's half of its breadth, so that is 50 mm. So that is y1 equal to, so its breadth is 100 by 2 for the first lamina A, B, C, D. So I've considered up to here. Okay, so not here. You can do this by considering here also. Thereby, the geometrical units will be changed for this second rectangle lamina. Whatever the method you can follow. So 100 by 2 is 50. Now multiply A1 into X1. So that is 20,000. So that is 2,000 into 10. So I'll write this value. Similarly, A1 into 50, that is Y1, around will get 1 lakh. So this is the value we got, the product of area and its y coordinate centroidal distance. So if you do the same for second lamina of rectangle CEFG, okay. So second lamina rectangle, it is also rectangle CEFG. So its cross sections are 60 into 20 as I written here. Okay. After subtracting 20 from this 80, we will get 60 into 20. So the area of this second lamina, length into breadth 60 into 20, so 1100 millimeters square. Similarly, we'll find the x coordinate and y coordinate distance for this second lamina. So x coordinate distance with reference to the leftmost line y axis, okay, will be half of its length, that is 60 by 2, then plus this 20. So maybe here, somewhere here, so x2 will be calculated like this. Okay, the distance from the reference line to its half of its length, that is 60 by 2 plus this distance. Okay, so this distance is 20. X2 is equal to 20 plus 60 by 2, that is 30 plus 20 is 50 mm. X2. Similarly, so y coordinate from the bottommost line of the L section, that is reference to XX reference axis, okay, will be equal to half of its breadth, that is y2. So from here to here, that is 20 by 2. Its breadth, this rectangular lamina breadth is 20. So the location of centroidal distance for rectangles as per geometrical considerations. So it's half of its breadth, that is 20 by 2. Based on that, we got 10 letter. Okay. So now multiply A2 into X2, that is 12 into 5. So 60,000. Then 10 into That is the area 2 into y coordinate distance. Okay, 12,000, 12,000. Yes. Now, so just add up these two. Okay, in order to calculate the centroid for whole lamina, whole L section lamina, we have found individually for each of the laminas. Now, we're going to calculate the centroid for the complete lamina, whole lamina. Okay, so now the summation of areas, that is sum of areas of these two, 1200 plus 2000 around will be 3200 millimeters square. So next we need these summations. Sigma of A into X is equal to 60,000 plus 20,000 is 80,000. Okay. Similarly, A into Y, summation of its product of its area into Y coordinate distances. 12,000 plus 1 lakh is 1 lakh 12,000. You can see this. Okay. Now, by known well formulas, okay, so we can calculate, we can find the position of centroid for this given unsymmetric section like L. Okay, so we know that from the formula for calculating the x bar, so summation of A into x by upon its total area. Okay, so let's say is given the value summation of area into its x coordinate distances for the L section. We found out by, okay, so 80,000 upon total area is 3,200. So by dividing these two, I'll get x coordinate is distance of, so 25 mm. So as I said, this is in mm cube, this is in millimeters per area. Okay, mm square cancel, only remains is millimeters. Okay, in the similar form, we apply the same to y coordinates with reference to x-axis. With reference to x-axis, so y bar is given by summation of area into y coordinate distances upon its total area. So that is, so y sigma of ay is given here 1,12,000. So upon its total area 3,000. So just will get after this then value of 35 centimeters. So in these cases, I mean the sections like unsymmetry in nature, we need to calculate both x coordinates and y coordinates in space to locate the centroid for given laminas or plane figures. Just try this x bar from the y reference y axis and y bar from the reference x axis. Let's locate it how it will be. So we know y bar is 35 mm. So from here to here we have 20. Okay, so there's just above that, right? Somewhere here, 20 or 35 means somewhere here, and then x bar is we got as 25 mm. Okay, so the thickness of this is 20. Okay, so just 5 mm beyond this somewhere here, right? So this is the centroid point C at a distance of x bar is equal to 25 and y bar is equal to 35 mm. Okay, so from this leftmost part and the bottommost part, y bar. So thereby we can locate the position of this centroid or the average point where the entire area, say 3,200 millimeters square, is assumed to be acting at this point for this L section laminas. Okay, I hope you understood all these three problems. It has an important problems. Okay, so T sections, I sections, channel sections, and unsymmetrical L sections we have discussed in the today's class. Okay, if you have any doubts, you can ask to me. I'm pleased to answer them. So thank you for your attention. Okay. Thank you. Ask any doubts in the three of the problems we have solved in the today's class.